screen. Okay, so far we solved problem 1 and 2. And 3, we will not solve it. In the last class, we already discussed it, that how you can solve it. Okay. So in the last class, we discussed that if a column is loaded eccentrically, that means direction of the load is not going through the centroidal axis or center line of the cross section, then how we can analyze the critical stress or critical load of a column. That we started, and all those free body we already discussed is in the class. And finally, we figure out this one, that bending moment in this free body, right, this value of m, we need to figure out. And this value of, if you take bending moment, right, this point, you will get this m equal to minus P into no, P plus P into Y. We already write over here. We cut the column right over here, make free body this portion, that right over here. Then we balance this point. This point, force will be opposite of this point. P downward, right over here, it will be upward. Bending moment clockwise, right here will be anti-clockwise. Then what we did, we cut the column at any point. We are saying cutting at a distance x, and that point deflection of the column is y, right over here. Then we try to balance it. This force working upward, so there will be equal and opposite force of P. Now, we don't know what will be the value of the moment, so we say only m. Then taking moment over here, we try to figure out the value of m. And that bending moment, we found that, why we say mx, because this value of m, if I take at the middle, it will be maximum, because y distance is maximum. And this value of m depends on value of x. Because if you cut it right about here, your value of m will be different. So that's why we put function of mx equal to p into minus p into e plus y. That value, we put it over here. So you get just mx equal to this value, you substitute right over here. Then you simplify y part, bring in the left side. So this will be your differential equation. And obviously, this is a second order differential equation. So you need two boundary conditions. So how we can solve this equation? Actually, this is not math class, so we will not solve it, but we will take help from the math. So we need two boundary condition. Number one, if x equal to 0, then y equal to 0. If x equal to L, that means you are right over here, still value of y will be 0. So this is not right. We need to put y equal to 0 right over here. Then you figure out the value of y from this equation, from the mathematics. We are not showing that how we'll solve it. Right over here, you get L by 2. This is actually L. So showing in small letter, it seems like 1, but this is actually L right over here. And P by EI is coming from this constant, okay, and this one minus 1. So this is value of Y, that means deflection. If you put x equal to 0, then you see this value becomes 0, because cos 0, x 0, cos 0 will be 1, 1 minus 1, 0, and sine 0 equal to 0. So this value will be 0. Again, if you put x equal to L, then you just simplify this equation, your y value has to be 0. Okay, but what location value of y will be maximum? Obviously, when length is L by 2. At the midpoint of the column, deflection will be maximum. So, if we put x equal to L by 2, that means y will be maximum or delta in the previous equation, this equation. Then you simplified the equation. Then you will get this equation right over here. Again, L by 2, this is actually physical length of the column, L by 2. So you see this delta, that means maximum deflection of the column at midpoint will be this value, okay? And from this value, we like to figure out that what will be the maximum bending moment. If you look right over here, this value of M, this M, we already figure out, right? M equal to, if we go back to previous slide, this M equal to this value. When Y value maximum, when X equal to L by 2, that means delta. So M will be maximum at, if I say M underscore max, that will be P, that means force into eccentricity E plus delta. What is delta? Maximum deflection. And this value E plus delta, we can figure out from this equation of maximum deflection. You see, when we need E plus delta, right? You look that equation, you multiply by E, both terms. So what are you getting? Left side, delta. Right side, you will get this value, minus E. So finally, you are getting E plus delta, right? And E plus delta equal to this mass that I put in the bracket. So PE into sec, this is L by 2, length of the column, okay? Now, there is a one question that you look in the previous equation, there is a negative sign right over here, right? But right over here, a max, I didn't put any negative sign. Because if you look carefully this point, there is a two force working at the where we make the free body, this point. If you look in this point, there is a two stress. One is axial compressive. So I can say minus P by A, right? Then you have bending stress. What is the bending stress? Sigma equal to MC over I, right? So that will be M star C by I. But I didn't put the minus sign yet, right? So if your column is, say, it has a width 2 inch or 1 inch and a buckle like that, then what will be happen? This side will be compression, this side will be tension, right? But P by A is always compressive load. So this one compressive, but this side, this will be tension, right? Just put positive sign. You look in the this point, still P by A will be negative. And this MC over I also negative, right? Because this is compressive side. So what does it mean? That means this inner side will experience more stress. So if it is break or cracked, we start from inner side. There is a maximum stress. So what we did, we just think this is a positive bending moment, and also compressive force is the positive. That's why we don't put the minus sign. So how much will be maximum stress at point where we cut the column? So our compressive stress will be P by A, and bending stress sigma equal to MC over I. And remember, this C is not the end condition. This C, say if we have a column, this type of cross section. This is neutral axis or centroidal axis. So your C will be distance from CG to the outer fiber of the column cross section. Okay, same as working beam. So you see that externally we apply only compressive force and we apply eccentrically. That means direction of load is not going through the CG of the cross section. As a result, we are getting a step bending. So there is a compressive component P by A, and there is a bending component MC over I. And when this will be maximum, sigma C, when M will be maximum. So where M will be maximum? Obviously at the midpoint of the column. So if this M we replace by M max, we get maximum stress in the column. Other thing that this I we can replace from here. I equal to K square into A from this equation. That we put over here. I equal to A K square. And we have a specific reason because M equal to P E into delta or this value, right? So if we bring P over here, and in the bottom already we have A. So P by A, we can take a common, okay? So let's go through the next slide. Now, in our column, we have C that we use as a end condition, right? So instead of this C, we put another variable, we call it C1. What is the C1? Distance of outer fiber from the neutral axis, okay? Then we replace I K square. This is the M. M max equal to this mass. This is our value of M max. And make sure you don't forget this is L actually. So all those value, this is value of M max. This value we put it over here. So you see this is the value of M max. We put it over here. P into E sigma. So If I pick up this portion and this portion is coming from M max. Then we take common P by A. Then we get this equation P by A into this mass. Okay. Now again this is L. This is length of the column. Then we can simplify it more. How? That this I equal to right over here K square A. If you put it over here and little bit simplified, I equal to K square A. So you'll get one more K over here. You replace this I. So 2K, okay, out of this square root. So we are getting this is L. And above formula, how we derive this formula? We start with a like pin to pin column, right? But there might be both and fixed. There might be one end fixed, other end free. We don't know, right? So for that reason, instead of L over here, we put LE because LE equal to, if I say LE equal to L by root over C. C is the end condition. So this equation, when you put L by E, then you can use for any n condition. So right over here, and this equation is known as second formula of column because there is a second over here. That's why, okay? And if I say this is X start from here, say this column length is 20 inches. Now you like to figure out the deflection at a distance 3 from the bottom. Say right over here, and this mass distance, for example, say 5 inches. How will figure out that this deflection value of y? This is our y equation, right? You just put x equal to 5 inches over here. Over here, then it will give you value of y. And y max, the maximum deflection at the midpoint, this will be this mass, okay? So how many equation we already got in the column? We got 3 equation. Euler equation of column for long column. Then we got short and intermediate column. We got Johnson equation, which is mentioned right over here. This is Johnson equation. And this is Euler equation. This is for long column. This is for short column. Now we have one more equation. If in both cases, like long and short and intermediate column, direction of load going through centroidal axis of the column. But if you apply load eccentrically, then you need to use second formula of column. Right over here. I put it over here. Okay. Now, if there is eccentricity is given, you immediately you jump on second formula. You don't need to think the column is a long or short. Okay, just use the second formula. And if value of eccentricity is not given, and you know that load is going through the centroidal axis, then you have two options, either Euler equation or Johnson equation. But how will know that I'll pick up Johnson or Euler? This is the condition. You need to figure out the value of L by K. Then this L by K is coming from N condition and material property. Then you figure out your own L by K. If L by K greater than this value, Euler equation is long column. If L by K is over here mistake, less than L by K, then you'll use short and intermediate column. Okay. Right over here, the second formula. Now we can solve a problem. Okay. You say it's saying an alloy hollow circular column of external diameter 200 millimeter, internal diameter 160 millimeter, and 6 meter long column. So 6 meter long, that means you are getting length of the column. Length of the column 6 meter. And column is circular but hollow, like this one. So outside diameter is given. This diameter is given. Inside diameter is given. So easily you are able to figure out the I of the column, right? Pi by 64. Then you say outside the d naught whole square minus inside the whole square. You'll get I. That is the I minimum. Because for circular cross section, Ix and Iy is same. And load is given P. This is value of P 120 kilonewton. At an eccentricity 20 millimeter. That means value of E is given. E is given, that means immediately you need to use second formula. And what they want? Determine maximum stress induced in the column. What will be the stress in the column? Given E value this much, and also find maximum deflection of the column. It's straightforward. So that means you need to figure out the delta max of the column. You need to figure out sigma critical of the column. How eccentricity you will count, calculate. Say this is the cross section of column, and this length, let me say this is 6 inch or millimeter, this is 4. I'm applying load right this point. Load is going through this point. And I'm saying location of this point from the left side is 4.5. Okay. Now you need to figure out what is the eccentricity of this column. Anyone? Nobody?
Sir,
Can I repeat? Okay.
Yes, sir.
You see, I give you column cross section is 6 by 4, right?
6 by 4. Yes, sir.
And I applied load in the column right this point. And I give you the location of this point. From the left side, 4.5 millimeter. Say
4.5 millimeter.
everything is millimeter. So what will be the value of E that I am asking you?
Sorry, sir, I am unable to answer.
You're not, what is your ID?
Sir, 135.
135. Okay, hold on. We are with section A, right?
Sir, B, section B.
We are in section B today. Okay. B 2921. Okay. Your ID?
Sir, 135.
135. Okay. Who can tell me what is the eccentricity over here? Anyone? No? Tuhin, roll 123. Tuhin, you here? You're not here. I'm not sure. You might went to Cox's after joining in the class. It's possible, right? Okay. 123, you're not here.
Sir, 123 has written in the chat that he is here.
He's here. Okay.
He has written in the chat box.
Written in the chat box. Okay. Hold on 1 second. No, he okay, Zakaria, roll
Assalamu alaikum, sir.
111. Walaikum salam. Tell me, what will be the eccentricity?
Sorry, sir, I am unable to see this portion.
You are unable to see. What is the eccentricity?
Sir, I am from Kustia, sir.
No, that's okay. It's from Kustia, it doesn't matter, right? We are taking online class. But what I am saying, cross section of the column 4/6 in millimeter. And we are applying load right over here, perpendicular to the screen. Now I am saying, is it going through the CG of the cross section? Is going CG? Yes or no? Roll 111.
Sir, I think
Is
it
going
will.
through, just tell me, is it going through the cross section of the CG? Yes or no? That you will say. I applying load right over here at point, say, C. Okay. This is C, point C. So if this point C is the CG of the cross section, yes or no?
Sir, I think it will.
It will. It is CG. Okay. Let's see. I can ask one more student. ID 129. Ishat Rafi. Rafi.
Yes, sir.
Tell me, point C is the CG of the cross section? Yes or no? No?
No.
Is it CG? Anyone who can tell me?
No, sir.
No,
No. It's not CG, right?
Sir.
Is not going through the CG. So what is the CG then? How much will be value of E? E mean eccentricity, right? What will be this value? We need to figure out in that case.
Sir,
E.
3 millimeter.
3 millimeter. No, 3 meter will be, CG will be right over here at the middle, right?
2.25.
2.25. I think it will be 1.15. You see, how much will be this distance?
Sir, 3.
3. So our eccentricity will be this much, right? So what is this mass?
1.5.
1.5. Okay.
Yes, sir.
So what is your ID? 129.
135.
1
35.
135. Good. Okay. So eccentricity will always count from the center point or CG of the cross section. So in this problem, already is given value of E, but sometime you need to figure out from the sketch or from the figure. Say I am giving you this kind of case, then I'm not giving this one. I'm just saying from here to here, this point distance is 4.5. What will be the E? You need to calculate, right? If you're not able to calculate, then you will not able to solve this problem. Okay, so let's see how we can solve this problem. Did you see the MathCAD file?
Yes, sir. Yes, sir.
Okay, so at first we see what type of data is given. So you see length of the column already given, it's a 5 meter. And it's a both and fixed. If both and fixed, then you can see in the on second, I can show you that is saying right over here. It is saying 6 meter long. I put over there 5. The fixed at both end. Okay. And so length is 6 meter. So we can change it to 6. And it will be automatically updated. Anyway, so both ends fixed, C equal to 4. P given 120 kilonewton. You convert in Newton. Eccentricity of column 20 millimeter. So you get value of E. Outer diameter given. You convert in millimeter. Inner diameter is given. You convert in meter. Then modulus of elasticity is given. Value of E convert in Newton meter square. What need to figure out? Maximum stress in the column and maximum deflection, sigma max. So since eccentricity is given, immediately you need to jump on second formula. So for second formula, this is formula for maximum deflection, and this is the formula for stress in the column. So you see in this for maximum deflection, you have I over here in the bottom. LE equal to root of L by root over C. So there is a K. So to calculate K equal to I should be minimum. That means I minimum divided by A. So you need to calculate the I area and also area. So this is area pi by 4 d naught square minus d square meter square. Moment of inertia pi by 4. This is hollow tube. So you need to minus outer diameter to the power 4 minus inner diameter to the power 4. So this is your value of I. Then what will be effective length of column? L by root over C. So that will be 3 meter. Okay. Now radius of gyration K equal to I by root over I by A. So you get this one. Now this C is the distance from the neutral axis of the column. That means you have a hollow, so your CG will be right over here. So value of C1 will be this much. So C1 will be outer diameter divided by 2. This is C1. Now you just hook up, all value is here. You just put here, you'll get this value. But you need to remember that if you use calculator, this value is radian. So you need to turn on the radian option in your calculator. Then you can convert, you can say sigma C you can say I convert in megapascal. Okay, it convert in Pascal. This one automatically given the value in megapascal. Okay, similarly, we figure out the maximum deflection. So I got in terms of millimeter minus 10 to the power 4. So you convert in millimeter. So 0.495 millimeter. Okay. So any question from this chapter from the column?
Sir, on
Yes.
page 39, will you please tell me about the C1?
C1.
Ji, sir.
Uh,
Sir, on page 39.
what do you say? ID.
Sir, on sir ID 111, sir.
Mhm.
Sir, page number 39, sir.
In the
Like, sir.
PowerPoint. PowerPoint.
Yes, sir.
Okay, let's see, let's figure out. Yeah. What is your question?
Sir, how can we get C1?
Page 39. 39, there is a two formula. One is Euler equation and one is Johnson equation. And over here, you see there is a C. Right? This C is the end condition of the column. And this C, you will figure out from 4 end condition that right over here from this table or figure. You need to remember. Okay.
Yes, sir.
Pin to pin is 1, but value of C1 is not the end condition. C1 is different thing because if you look in this free body, there is two type of load, right? And this load you cannot see from the outside. Only you can see this P1 from the outside. But internally, inside the material, it experiences two forces. One is compressive, other one a bending moment. If
Yes, sir.
there is bending moment, what can stress develop? Work like a beam, sigma equal to mc over I. And due to the compressive stress, there will be P by A, right? Because directly is normal to the cross section. So that's why you look in the bottom formula. This is our formula. And in this MC over I instead of this C, I can put Y. What is bending moment will be maximum? If your cross section is say rectangular, and this is your neutral axis, this is your CG, then this distance, that means bending moment at the outer fiber always maximum. Where is the bending moment 0? Anyone? Not bending moment, bending stress. What location bending stress is 0? Anyone?
Sir, middle.
At the neutral axis. Good. Your ID?
131.
131. Okay. So you see sigma equal to MC over I. Right over here, value of C is 0 at neutral axis. So stress will be 0. Gradually you moving upward, C increasing. Right over here, value of C maximum. So bending stress over here will be maximum. You go downward, same thing. Over here will be maximum. If this one tension, this will be compression. Or this is compression, then this point will be tension. So that's why there C, I put C, you can put Y, whatever you like. So this C and the N condition, both are not the, though letter is same, but they are not same meaning. If I put Y, I can say my by a k square. Now, instead of Y, I put different constant. I put over here C1. Instead C1, you can put anything, Y1, okay? And this C1 is the distance from the neutral axis to outer fiber, okay? Is it clear?
Sir.
Clear
Yes,
now?
sir.
Okay.
Yes, sir.
Anyone? Any question? Okay. There is one more column that you have a very short column, and you apply load at the eccentricity, certain eccentricity. In that case, column, it don't buckle that much, okay? But it fail by only compressive stress, that is called strut. Strut, STRUT, okay? And that one normally I teach in the machine design, okay? We will not include that one. So in this chapter, there will be one math on derivation, either Euler equation or derivation of Johnson formula. Then there will be one math, and there will be some, might be 2 mark or 3 mark short question, okay? So this chapter is finished. So anyone has any question? No? Anyone? Anyone? No?
I guess no, sir.
Okay. And our class until how long?
Sir, we have one more slot.
Almost slot, right?
Yes, sir.
So I am giving you 5-minute break. Right now, 150, come back 155. Okay.
Okay, sir. Okay, sir.
Then we will start the next. Okay. I am back. Are you able to hear me?
Yes, sir. You are audible.
Okay. Okay, good. Let me share the screen. Okay. This is the new chapter. It's called torsional shear stress. Torsional, right? From the word torsional, you can imagine little bit. Say someone, your friend, holding your hand and pulling. That will be, so what will be load on your hand? Tensile load, right? But instead of pulling, say this is your hand, you have knee right over here, a joint, right? Then your upper arm, and you have finger right over here, whatever. Okay. Now, if someone pull you, your hand with force P, then stress in your hand or in your bone will be P by A, cross-sectional area of your bone and muscle. But instead of pulling, if he twist Bangla Mosrano, then what possibility have happen? Right over here, your hand might be breakdown. Okay, so the kind of this is twisting, right? For example, if you take a writing chalk that we write in the blackboard, it's a kind of round cross section, right? And by you taking in the hand and do like that, the opposite direction, it twists little bit, you will say it become just two part and break down most possibility at 45-degree. Okay, because at 45-degree shear stress is maximum. So if you apply torque on a body or torsion on a body, then it experience shear stress. So what is shear stress? Anyone? Shear stress tau, normally we express by tau, right? Equal to shear force divided by area. Say I have a pencil, I am pulling, this is not shear force because this is normal force, sigma equal to F by A, that you can figure out. But what is the shear force? If I apply force parallel to the cross section, say I have a vegetable, I just do like that with a knife, then what will happen is that become two part, right? That means that shear force or parallel to the cross section. So when a body become two part, if their shear stress is work, then it become two part. And so if you take a chalk pencil and you just twist little bit, and then you will see it break down like this, right over here, become two part. So why it break down? That means when you twist, then inside the material, some internal force work, and that force working parallel to the cross section. Okay. Now, you take a chalk pencil, you twist, it become two part, but same size, same diameter and length. If I give you a little bit harder material, say I'm giving a rubber rod, still you can twist, right? It might not break down. Then if I give you a steel rod of same size, even if you do like that, it will not break. What does it mean? Why? Because you externally you apply torque, so it generates shear force. That means your torque try to break the object in two parts. That means you generating some force parallel to the cross section. That force try to divide the part into two, but material has a internal resistance. He'll say, hey guy, don't try to twist me. Okay. So if that resistance become higher than your applied torque, then what will happen? It will not break down. But when your applied torque will be higher than the material resistance, then your parts will be breakdown. Okay. So normally torsional shear stress, and for example, there is a other thing happen. It will break down. Then other thing happen is called angular deformation. You say pencil, you take 8 or 10 pencil, put a rubber band close together. Then what will happen? You will see you try to twist. Then you see at the outer pencil, they moved little bit. That means what I am saying, after torque, you will see pencil before deformation. They were all the pencil was straight, but when you apply the torque, say this is the pencil at the beginning, it was straight, but after you apply torque, it move like that. Okay, that means if I draw over here, it just remain come over here. That means it moves little bit. That is called angular deformation. But we will show you later on. Now, why we need to study this one? What is the
স্যার একটা
application?
কোশ্চেন ছিল।
Okay, go ahead.
স্যার বললেন যে ইন্টারনাল ফোর্সটা প্যারালালি কাজ করবে।
Yes.
প্যারালালটা কিভাবে কাজ করতেছে এখানে?
Parallel to the cross section. If you cut right over here with the knife, then this will be your cross section, right? Still, it will be round. So your left side torque is this one anti-clockwise, right?
জি
So right over here, he will try to resist. So this is anti-clockwise. Over here, torque will be clockwise. But this torque you cannot see from the outside. If I imagine there is some area right over here, this is circle, right?
জি
This circle I am drawing a little bit bigger right over here. So when you apply the torque, then if I say some area right over here, small area dA. So you apply the torque, what does it mean? You try to twist.
টুইস্ট
Your friend coming, holding your hand, try to do like that. Then you will see if he is more energetic, he can twist, he can break right over here. That means your muscle will twist little bit, right?
জি
So
স্যার
that means if this is the center, you apply torque, then some force will work along this direction, along this direction, along this direction,
জি স্যার
along this direction. So I am saying I took the very small area. So this force is dF. If distance of the small area from the center is rho, so what will be torque? dt. Torque will be force into distance. So your distance is rho. So torque will be rho into dF. Okay. So this dF is the internal force. If your applied force, say this is applied force, applied torque dt, this dt will generate this much force inside. but material has higher resistance, then what will happen? It will not break down. But if you increase the torque again higher than the internal resistance, then it will break down. Now you see, what is the DF? What kind of force? This DF. DF actually shear force. And how we can figure out the shear force? Shear stress equal to shear force divided
Divide
by
by area.
area. Now see this DF, I can, instead of DF, I can say shear force equal to small force, shear force DF divided by dA. So DFS equal to tau into dA, right? This value is coming rho into tau into dA. So what will be the total resistance over here? Your dt. So if we integrate left side d, right side will be area integration. Okay. Yeah, we'll discuss more, then hopefully it will be more clear to you. Just right now, you remember that when you applied the torque, it tried to create a shear force inside the material. So what is the function of the shear force? It tried to divide the material, and it always work parallel to the cross section. Okay. Now, so when we apply torque, then shear stress developed in the circular cross section, and when is subject to twisting force. Couple or torque, that's is showing that one end T prime, other end is T. These couple have a common magnitude of torque but opposite of direction. Now, why we are studying? If you see how in your house you have the pump, right? This is your pump. Say left side is a motor. What happened? Motor try to rotate the shaft, right? And the pump, then pump impeller rotate, right? So if this shaft is very brittle material, what will happen? You know, it will break down immediately. Similarly, you see, if you look in the truck chassis, sometimes you might see you walking in the road or traveling in a rickshaw, you see truck going with empty chassis. You see there is a shaft from the front engine to going to the rear axle, and this is rotating.
Yes, sir.
So if this is breakdown, say you make it very soft material, what happened? This is twisting, right? There is a differential gear. From that gear, force is going left wheel and right wheel. But if this is breakdown, is very make with the very soft material, then you immediately engage the gear, shaft will be rotated, but it will not able to carry the load. It will break down. So that's why again your crankshaft, engine crankshaft inside, this is a round shaft. So there is a lot of application of round shaft that transmit power from one point to another point. And when I saw in our village, okay, in the rice mill, say they have a bigger engine, IC engine, and from the belt, they are rotating a shaft over here. And in this shaft, they have several pulley. Okay, in that pulley, they have a V belt. Right over here, they have another machine. But same IC engine, they have 2 point you can use for in the for break to have the rice from the rice shell. You just take out the shell, you get the inner part, right? So you will see they use a bigger belt over here. So what happened? This shaft, its shaft is very weak. It will break down immediately. So as a engineer, say you are designing a big ship and you should have a bigger engine. You figure out the horsepower, then how will you rotate the impeller? What is called right in the backside of the ship? Propeller. You have to rotate this propeller. So shaft of the propeller will be attached with the engine, right? So if this is very weak, then it will break down. So those are the engineering application. Okay. So just remember two things, that if you apply opposite torque in a parts in the round shaft, then internally he will feel shear force and try to break the shaft into two parts. Okay. So when you designing a shaft to transmit torque from one point to another point, you need to make sure it is not breaking. Okay. That's the purpose for this chapter. So common application of transmission shaft you will use in the turbine motor, motor to machine tool, then a rear axle of an automobile. So those are the example of application of torque in a circular shaft. Right over here showing the example. You have turbine, right over here generator. So turbine rotating, shaft rotating, right? So if your shaft is very weak, then it will immediately break down. Okay. And you see right over here, for example, you take 40 pencil and all of them, say all of them is pencil, if band with the rubber. Almost our pencil is 12 inch long or 10 inch, right? Then you twist, then you see initially they remain straight, but after you twist, then what you see? You look this one, he was initially straight, right? Initially his length was from here to here. Oh, this is too bigger size. If I take the red one, so initially it was straight, but after twist, he moved, come back over here. Okay. And you can test it in home. And other thing you will see that say you have 40 pencil, then you put in a rubber band, multiple rubber band, try to twist. Then you see all the outer pencil, they rotate. They moving like that one in the bottom picture. But inner pencil still remain straight. So what does it mean? That means in the inner pencil, it don't experience that much shear force. Okay. Similarly, in a beam, in the neutral axis, bending stress is 0. So similarly, from the center pencil, you'll see it is not rotating, remain straight, but from the center to the outer pencil, you see they are moving further from the initial position. Excuse me. Okay, so when a twisting moment or torque applied in a circular shaft, it resists the torque by shear stress and angular deformation. What is angular deformation? Right over here, I am saying that this pencil initial was straight, but after deform, he coming right over here. So He creating an angle, right?
Yes, sir.
This angle is called angular deformation. Hold on 1 second. So what I like to say that when you apply torque, two things happen. It will generate shear stress inside the material, and also it is deform the material. Similarly, same thing everywhere. If there is a stress, there will be deformation. Similarly, you have a beam, you apply load, you bend like that, right? That means there is a stress and deformation. Similarly, you have a column, you apply compressive load, it deforms. That means there is a deformation and also stress. That we figure out all the formula. How can figure out the stress and how much the deformation value of y. Similarly, in the beam, you figure out the formula sigma. You figure out the shear stress, then you figure out the deflection of the beam. So similarly, when you apply a torque in a circular cross section, then torque will create shear stress inside and angular deformation. Angular deformation that has other name is called shear strain. So what do you need? We need to figure out a formula to find this shear stress tau. And also we need a formula for angular deformation. If angular deformation is theta, we need to figure out this value of theta. So this theta equal to TL divided by Gj. T is the applied torque, L is the length of the shaft, J polar moment of inertia, and G is the shear modulus. Similarly, this tau equal to T into R divided by J. These two formula. Now, this I just giving you, right? But you need to know how this formula is coming. Because inside, outside, you apply torque, how tau is coming, R and J, then G, then theta, right? So in this chapter, we'll derive these two formula. So before we derive, you look that angular deformation, that means angle theta, it depends on the magnitude of applied torque, length of the shaft, what type material you use, and also size of the shaft. And shear stress developed inside the shaft, it depends on the magnitude of the applied torque. Size, that means radius of the shaft. And one thing you need to remember, that shear stress at the center of the shaft is 0. And it increases gradually from the center to the outside. At the center, shear stress will be 0. Then gradually you move from center to along this direction, then your shear stress will increase. Okay. Why? Because I already show you that if you bundle 40 pencil or 20 pencil with a rubber band, then you will see at the center there is no deformation. But outer pencil, you will say they have more angular deformation. That means outer one will experience more shear stress and inner one will experience less shear stress. Similarly, a shaft, you can imagine that has a million of fibers attached together with the rubber band and to have a round shaft. Okay. So let's see, before we derive, I already told you that if you apply torque, it try to generate shear force inside the material. So this one, a shaft, there is a counter and the clockwise torque at point B. At point A, clockwise torque. So both are same but opposite magnitude. If it is a made brittle material, it immediately break down. Now we are imagining why. Why break down a material? Because shear force working. So if shear force always work parallel to the cross section, so we are thinking a small area dA over here, and he expressing a shear force. So that means this torque is clockwise, right? So all the force working tangentially from the center at a radius rho. And you see, they also trying to rotate along this direction, all the force, right? And how will be torque? If force dF create torque dt, then this dt equal to rho into dF. Okay, so this one we needed, we will apply in the when we derive the main formula. Now this dt you are getting for small force working on a area dA. Now how we can get the total torque? You just integrate total torque equal to integration of rho dF into area integration, because dF working in a small area, and this dF we can substitute by tau, because dF equal to tau into dA. So this tau dA we can put over here, then it become area integration. The same thing we just put over here, that this torque equal to rho into dF integration and dF equal to tau into dA. So torque equal to rho tau dA root over. Okay, I'm sorry, integration. Okay. Now, before we just discuss about the fundamental things, that why we are studying this chapter, what is the torque and what is its function, and what type of parts carry the torsional load, that we show you the shaft of a automobile, or you shaft of a pump and motor, and other, say you have a generator and turbine. In that case, you need to design the shaft, right? So now we will derive the formula that I am applying torque in the shaft tau, I'm sorry, torque T, then how much shear stress will develop inside? Our formula is this one, tau equal to T into R. R is the radius of the shaft divided by polar moment area. So this formula we will derive. So before we derive, we need to make some assumption. So what we'll do, we'll take a round shaft. Sorry. We are thinking length of the shaft is L, and torque applied in a round cross section bar, or you can say shaft. Material of a Hooke's law, you can say material is homogeneous and isotropic, although I didn't mention, okay, but you can mention on things. but subject to pure torque. What does mean pure torque? That means no other force working here. Only torque is working here. Okay. And adjacent cross section, originally plane and parallel. That means all your cross section of the shaft or bar is uniform, is not tapered. Okay, that is saying. And cross section remain plane and parallel under torque. That means after you applied the torque, the cross section, you applied the torque, right? But still this cross section remain, say, like this one in the plane. Like if I say, if I cut it, there will be vertical plane, right? So it's saying all the cross section will remain in a plane. It don't mean that your cross section will become inclined. Say if it's very soft material, then what will it's going to squeeze before fail. Say you take a rubber shaft, you apply torque, then it will be squeezed somewhere. Squeeze, that means your cross section will not remain in a plane. It might be inclined a little bit. That is saying that cross section remain plane and parallel to each other under torque or after applied the torque. Radial line remains straight. Radial line means line passing through the center of the body in axis of symmetry condition. Now, so in this shaft, length L and torque right over here, apply clockwise, right? And other end applied anti-clockwise. And there is a one thing that you have torque along this direction, anti-clockwise, right? This torque you can express by double arrow or by single arrow. Normally we express by double arrow, okay, by thumb rule, right hand rule. So this is clockwise, right? I do like that. My hand is going, my index finger is going, thumb is going outward, right? So that's why this torque they are showing right over here. And this one is clockwise. That means I am doing like that. So this thumb going outside, right? That means this is direction of the torque that are showing over here. That means a torque you can represent by this kind of arrow, like this one, anti-clockwise, or you can show it by arrow. And some book they show it by double arrow. Okay, so in this book they are showing the arrow over here and there is a torque. Okay, so before applied the torque, the line AB is remain straight, but when we apply the torque, the line AC, this is our C, this is A. Point C, we move to coming C prime. So what happening over here?
The angular deformation.
Angular deformation gamma. Good. So this gamma value we can figure out. If we apply tan gamma, I is saying tan gamma equal to, what is the definition of tan? Perpendicular by base. So this will be C prime divided by line AB, AC. AC means length of the shaft. Okay. So you see, but this gamma value will be very small. So if gamma is very small, in that case, tan gamma equal to gamma, then we can say equal to C prime divided by L. Now I like to figure out this C prime. This C prime, you see, this shaft diameter radius is R, then what will be the arc length? This length, CC
Arc.
prime. r into theta, right? Because
Yes, sir.
is making angle theta. That's why gamma equal to, we can say, r theta divided by L. Okay. So it will explain in the next slide. Let's see. Right over here, all the term, it's what is the J, assuming J is the polar moment inertia of the bar, R is the radius, rho is the radius at any point of the cross section. That means if you cross section, right, this is the center, right over here, radius is R from here to here. But if you take a point right over here, then the radius of that point from here to here is rho. That is saying over here is rho. T is the applied torque, gamma is the shear strain of the shaft. Now it's saying due to the application of torque, line AC moved to a new position, AC prime. That means C point coming over here. To apply torque T. Same figure, just we already figure out that gamma equal to r theta by L, because C prime, you see this one, we create angle theta, that we figure out. Gamma equal to r theta by L.
Sir,
Now, yes,
sir, here theta is the angle between C and C prime, and
yeah,
gamma is the angle of deformation, right?
gamma also angular deformation, but over here, gamma actually is the shear strain.
Yes, sir.
You remember in the beginning of the solid mechanics, say you have a straight bar and fix at the bottom. Now kicking right over here. After you kick, what type of force you apply? Obviously shear force, because your
Shear force.
parallel to the cross section, right? After
Yes,
you
sir.
apply shear force, it's not breaking, but it deform like that. That means this much deformation. It is also angular deformation, but we call it shear strain. So this gamma actually is the shear strain, and this theta actually is the angular deformation.
Deformation.
Okay.
Yes,
So
sir.
there is a little bit different from this gamma and theta. Both are not the angular deformation. Gamma is the shear strain, and theta will call it angular deformation. Because
Deformation.
this gamma, what is the modulus of rigidity? Shear stress tau divided by shear strain is called modulus of rigidity. So by using this relationship, you'll see next time we'll try to figure out a formula to find out the theta. That means theta formula will come like TL divided by GJ. Okay. Anyway, we'll discuss later on, then it will be more clear. So
Yes, sir.
what is our target? Our target to derive this formula. Tau equal to TL, I'm sorry, TR divided by J. So far, we are not make any relationship between the tau and the torque, right? So what we are thinking that after I applied the torque, right over here, if you take cross section, in that cross section, if you take it experience some kind of shear force, DF. From that shear force, we'll figure out the torque. So it's a shear strain of longitudinal fiber, and shear stress in the shaft varies linearly as the distance increases from the center. I already told you that you move from the center, shear stress will be gradually increase in the shaft. Shear stress in the shaft also symmetric around the geometric axis of the shaft. What does it mean? That means shear stress right? This point and this point will be same because this is symmetric from the center. If their radius is same, then it don't matter what they remain. The value will be same. So what we are thinking, we're thinking a small strip. The thickness of this strip is d rho. D rho, and inner, this is a ring, right? Small strip. Inner radius is rho. We'll try to figure out that how much force is working over here did we apply torque T. And this torque will create shear force on in all the area, right? But we are thinking how much will be shear force right in a small area. So at radius rho, but the radius of the shaft is r. We are thinking only this much radius is the rho. So we already show you that dt equal to, right over here, we take integration the left side, right side you can say dt equal to rho tau into dA, right? So that we will apply right over here. So we are thinking that what will be this torque will be in this small ring. So dt will be tau rho dA. Now what is why tau rho dA? How it is coming actually? Because it's coming actually dt d into t that equal to df. Second, d df into rho. This one, right? Equal to df equal to what you can say? Tau into area. So there will be tau into area means small area, dA. So this will come dA into this rho, R O U. That's right over here. But instead of tau, they writing tau rho. Why? Because tau vary with the rho. Tau maximum at the outer fiber. Gradually you come to the center, become 0. That's why they're saying the at radius rho shear stress is tau rho. The into rho into dA. That means this is your tau dA rho. This is the torque. Now, if you integrate both sides under area, then you can figure out the total torque. So let's see how we can do it. What will be the small area dA? This small area. This small area. How can figure out? Anyone? If I cut it right over here and try to make it straight, then what will you get? You will get a long strip like that, right? What will be the thickness of this strip? D rho. And what will be the length from here to here? What will be the length? Anyone? Length will be
2 pi r.
2 pi r. Good. 2 pi r will be length, and the width will be d rho. So we will get the area dA. So that is the d over here. This is the small area dA equal to 2 pi rho. Instead r, we will use rho into d rho. Okay. This is one thing. Other thing, we know that tau directly proportional to the rho. Is radius 0, tau 0. Radius increase, tau increase. So tau proportional to rho. From here, you can say tau equal to rho into some constant. That means tau by rho is constant. So if I say at the outer fiber, radius is r, what will be shear stress? Tau r. And at the radius rho, shear stress will be tau rho. This is constant. Always ratio will be constant. Now, in this previous formula, right over here, we can figure out the value of T. How? If you do, you see, now this dt equal to coming tau, subscription rho, tau rho, right? Star rho, star dA. What is dA? 2 pi
Rho.
into rho, right? Rho into thickness. What is thickness? D rho. Now, if you integrate both sides, then you will get the value of torque. That we did over here. Right over here. The integration 0 to r. Why 0 to r? I'll tell you later on. You see tau rho to pi r d rho. You see, if this rho, what is the value of the rho at the center? 0. Value of outer fiber, rho equal to r. So if we integrate 0 to r, then we get this value. We get this one. Now we need to just integration and some simplification. You see this tau rho. What is the maximum? Outer fiber is the maximum. So I need to take out the tau rho. Tau rho I can take out from here. Tau rho equal to tau rho into tau r into rho divided by r, right? That we put over here. And this part remain the same. Now you see our integration tau r and 2 pi, it will go outer of the integration. And inside remain rho to the power 3 into d rho. And integration limit 0 to r. So after integration, you get this one and then r to the y 4 by 4. Then you just do the sum simplification. After simplification, tau r by rho, you get this value. And this is equal to polar moment of inertia. That means you are getting tau r into j divided by r. And left side, we have torque T, left side. Right over here just is showing that how j equal to pi by 32 d to the power 4. If you put d equal to 2r, then you get this value. That's why instead of this value, we put letter j, polar moment of inertia. Now from here, you just figure out the tau. So tau equal to t into r divided by j. That we have right over here. Tau equal to t r by j, where j is the polar moment of inertia and value of j is mentioned. So in general, you just put instead of tau r, we can say tau equal to t r by j, where r is the radius of the shaft. If you figure out the shear stress at the center, what is the value of r? 0. So tau will be 0. But at the outside, shear stress r value is maximum, then shear stress will be maximum. Any question? Any question from here? No? Hello?
No, sir.
No? Okay, I think our time is over, right? After finishing this slide, then we'll finish it. You see tau distribution. You see tau along vertical axis, tau. Horizontal axis, radius. So you put radius 0, R0, shear stress 0, over here will be 0. Then R gradually increase, shear stress increase. At the outer fiber, it will be maximum, because if you put R equal to maximum value, tau will be maximum. So this is the distribution of the your shear stress in a solid circular shaft. If you have a hollow shaft, then this portion no material, that means there is no shear stress, right? So for point C1, your shear stress, you just put it over here, inner radius. For outer fiber, you put the outer radius. Okay. So far, any question? No question? So
No, sir.
this is the, right over here, this is the torsional shear stress distribution in a circular shaft. Sometimes we put question for 2 mark. What is the distribution of shear stress in a hollow shaft or in a solid circular shaft? Okay. So we can stop it right over here.